Hey everyone, welcome to our channel After School. This is Gayatri Patel, your physics ma'am. So guys, how are you all? So in this video, we are mainly going to discuss DS board, AP board and also CBSC board's class 10th important chapter, that is electric current. Yes, so in a boards, TS and AP boards, we have it with the name electric current, but in CBSC, it is named as electricity. Okay, both are of same chapter, so no difference at all, not even a single concept. Okay, all these boards class 10 students can watch this video. And in this video, we are going to revise electric current full chapter, full revision in only one video, right? So if you feel this video a bit lengthy, then you can keep watch this video by keeping playback speed in 1.25x or 1.5x. Got it? And also, I'll mention each timelines of timestamps of each and every concept. Okay, so you can easily move that video to that particular concept and revise it. Okay, now without wasting time, let's get started. So this chapter starts with the concept electric current, but to understand electric current, you need to know what is electric charge. Okay, now what is this electric charge? Why do we need to know about electric charge before going to learn about electric current? So there is a connection between charge and electric current. Okay, now first of all, what is this charge? Okay, so you may already know that for every matter, for every object in the universe, fundamental property of any body is mass, right? So same like mass, electric charge is also a fundamental property. So it is a fundamental property of an object. Okay, got it. Now, what is this charge? How do we know about charges? Okay, so these charges present in these are very elementary particles. Okay, if you go into the any deeper level of any object, then you can see some small molecules or atoms, right? So these particles are arranged in a molecule or any atom like this. So for example, if you consider this as a nucleus or center of any object, and this is any one of the orbit around a nucleus. Now, so in these charges, so here it is nucleus, so it is called as the center part of any atom is called as nucleus. In this nucleus, we can see two types of charges. So what are they? Simply, they are nothing but neutrons and positive charges. Okay, now these positive charges are known as protons. Got it? Now, around this nucleus, there are negatively charged particles which revolves around it. Okay, negatively charged particles. These are known as electrons. Okay, electrons are basically negatively charged particles. So now we got to know that charges, there are three types of charges. So first is negatively charged particles and positively charged particles, and also there are no charge of for these neutrons. Okay, they have no charge. Okay, I mean they are completely neutral. Okay, we can see neutral. Okay, these are of neutral charges. Got it? Now, they have some properties. Okay, what are these properties again? Simply, for example, if I just bring positive charge and positive charge together, then what happens? These two charges will repel each other. Okay, now I'm just bringing one negative charge and another negative charge together, and again here too, these two charges are repelling each other. But what happens if I just bring one negative charge and one positive charge? Simply, here these two charges attract each other, right? Now, by this, what do you understand from this? Simply, so these are, what are these charges? Like charges, right? If I bring like charges, then both these charges are repelling each other, right? So like charges repels. Now, what about here? What's happening here? So when I bring two unlike charges together, that means one plus charge and one positive charge and one negative charge, these two charges are attracting each other, right? So here I can say Unlike charges, attracts, right? That's fine. But what about this electric charge? Electric charge is a physical quantity, right? So any physical quantity has some units. Then what about units of electric charge? That is nothing but coulomb. So what are the units of electric charge? It is coulomb. Okay. Now, what is the charge of one particle? So here you can simply say one electron. One electron is equals to 1.6 into 10 to the power of minus 19 coulombs. Okay. In 1 coulomb, we can see these so many for electric charges, but in one electron, one positive or negative, one particle's charge is 1.6 into 10 to the power of minus 19 coulombs. Got it? This is about electric charge. Now, if you consider any conductor, okay, now we are going to discuss electric current. So, in order to discuss electric current, just discuss the behavior of these charges in any conductor. Okay. Now, for example, here I have considered a any conductor, right? So, in this conductor, how many charges will be there? So many, right? We cannot even take a number. So there are millions of charges will be there. It can be a positive charge, it can be a negative charge. But what about the motion? Okay, they have some motion, right? Then how these positive charges and negative charges will move in this conductor when it is not connected to any source or any battery? Simply. So this is given by this information is given by Drude and Lorentz. Okay. So what this theory is saying that when a conductor is not connected to any other source or any other battery, then all the particles in all not all the particles, all the negative charges or free electrons or free charges have a random motion. Then what about positive charges? Simply. So in any conductor, positive charges have a specified allocation of any. Okay, these are all positive charges are allocated. Let's say these are allocated in the spaces. So this special allocation of these positive charges is known as lattice. Okay, lattice. So these positive charges are fixed in this lattice. So they won't move. They won't have any motion from this lattice point. Then what are the charges which are in motion in conductor? They are simply these electrons. So the electrons are revolving around these positive charges, right? So since they are free, so free means loosely bounded electrons or the electrons which are in the outer orbits. So you might have studied it in the chemistry that all the electrons are revolving around the positive charges or nucleus in different orbits, right? So if an electron is revolving in outer orbit, then it is able to move from one point to another point or one atom to another point, right? So those are known as free charges, right? So now if I consider a negative charge here, then it will move randomly from here to there, like this. It moves like this. So when it is not connected to, when a conductor is not connected to any other source or battery, then it has, electrons has random motion, okay, or disordered motion, we can say random motion. Now what happens about net charge in this case? If I just take any cross section, okay, for example, now here I have taken a cut or a cross section at this point, okay, now of cross section area A. Now what happens net charge through this area? Simply, for example, if 5 electrons are moving from this point to there, okay, or let's say ends A and B, okay, now 5 electrons are moving from A to B, then same, since it has a random motion, then same 5 electrons are also moving from B to A, right? Now the net charge here, what happens? Net charge is always number of charges going to that area. But here, if we take sign, then what happens? First, 5 electrons are going from A to B, right? 5 electrons, and another 5 electrons are going from passing to this area from B to A. Since it has an opposite charge from this 5 electrons, so I can say it has negative charge. So 5 electrons and 5 electrons, it is zeros, right? So net charge here is 0. So not only 5 electrons, you can also consider n electrons. So here also this here to B to A, n electrons are going, right? Anyway, whatever the number, but the same number of electrons are going from A to B and also B to A. In this case, net charge is always zero, right? But what happens if I connected it to a battery? So this is all happening when it is not connected. It is not connected to battery or source. Any battery or any source, right? Then what if it is connected to a battery or a source? Then what happens? So to understand this, let's just take a small circuit, okay, where you have studied it in your 7th class or 6th class. There, a basic circuit you all guys know, right? So that is nothing but simply we have taken a battery. Yes, I hope you know what this symbol means. Yes, it is a battery and this is positive terminal and it is a negative terminal, and I have connected it to switch, and then I have connected this bulb to our circuit. Now let's it ended. Okay, this is switch and it is battery and this is our bulb, right? Now if I connected if I just switch on this circuit, then what happens? Circuit will be closed and this light bulb will glow, right? Now what's happening here? Just now we have studied that it is a conductor. I have taken a pure conductor. I hope you know what is conductor and non-conductor or insulator. Yes, we'll discuss about conductors and insulators in this chapter only in later concepts. But here, as of now, conductor is a material which allows the current to pass through it. Okay. So all metals, we can consider it as a conductor, a very good conductor. Fine. Electrical conductors. Now I have taken a wire, okay, electric conductor wire, and I have connected it to a bulb and then battery. Now what's happening here? If I just switch on this circuit, then current will pass through and this bulb will glow, right? But what if I have switches in off position? In off position, the bulb will not glow. Then what's happening? Here you can consider that when switch is on, okay, when switch is on, bulb glows. Bulb glows. Then if it is off condition, then it is off, then it won't glow, right? It won't glow. Now what's happening here? Why it is glowing when the circuit is closed and it is not in off? Simply here, when the circuit is on, then electric current is passing through it. Okay, or we can consider that some energy is passing through it. Fine. So that is why this bulb is glowing. But if it is not connected, just now we have studied that no current is passing through it because no charge is flowing through, right? Net charge is 0 in that case. That means when it is not connected to a battery. But here I have connected a battery, right? Now what exactly is happening inside this conductor? So here I am just explaining again while taking a conductor. Okay, here I have taken the same conductor, okay, of ends both A and B, right? So yes, in this positive charges are all fixed, right? All the positive charges are fixed. Now there is no hope of positive motion of positive charges because they have a fixed locations. Now it's time to discuss the negative charges, the electrons motion. So now what's happening here when it is connected, when the switch is closed, okay, when the switch is off in on position and then circuit is closed, energy is passing, all these charges are taking energy from this point to the bulb, right? Then only here this bulb, we will be able to see bulb glowing. But in order to take energy from this point to this point, now what's happening? All these electrons, okay, all these electrons are moving in a specified direction. That means now they have a direction. Okay, all the electrons are moving in a same direction, right? Now, if I just take a cross section just like earlier, if I just take cross section just like earlier, then what happens? Since all these charges are moving in a same direction, so I don't get the net charge 0, right? So here I'll get non-zero net charge. For example, from this point from A to B, n number of charges are moving, okay, through this cross section A. Now, what's my net charge? Net charge here I'm considering as capital Q. Capital Q is equals to n electrons. So there are no charges are flowing from B to A. So I'm just considering 0. So this is net charge flowing through this conductor, right? So through this conductor, through this charge, this energy is moving from, transferring from one point to another point. So this charge, so net here, what's happening? Some amount of charge is moving through this area. Okay. If I consider this amount of charge per unit time, then it will give us electric current. Now, have you understood the relation between electric charge and electric current? Yes, now here I am giving you the definition of electric current. So what is electric current here? So electric current is a physical quantity, okay, and it is denoted by the symbol I. So what it simply gives, it is nothing but, or it is defined as charge per unit time, right? So I can write it as I is equals to amount of charge per unit time. Fine. Now I hope there is no need of me to write whole definition here. So I'm simply, since it is a revision, okay, since it is not required the full definition, so I'm just giving you simply telling you the definition. So that is, electric current is a physical quantity and it is the amount of cross section, the rate of change, the rate of flow of charges per rate of flow of charges. Charges through given cross section. Okay. So we are measuring all these charges, motion of these charges in given cross section only, right? Through given area or area of cross section you can consider. Okay. And this electric current has, these charges has direction. So electric current has both direction and magnitude. So we simply say 5 electrons are going from going through this area and 10 electrons are going through this area, right? So that means 10 electrons is a magnitude. Okay. So electric current has both magnitude and direction, but still it is a scalar quantity. Okay. Electric current is a scalar quantity, but still it has both magnitude and direction. Okay. Now what about the units? So in order to know the units, you can simply follow the formula. Okay. Here it says formula, right? So I can write I, capital I is equals to, what is amount of charge here? I can write amount of charge Q is equals to NE, right? So charge numerator Q by T. Okay. So this is the formula for electric current. It is very useful if they have given you any numericals in the question paper. Fine. And from this I can write Q is equals to IT, right? And this is again one more relation, okay, which is derived from this. Now what are the units? So in order to find the units, you can simply write the units of numerator and denominator here. So what are the units of electric charge here? Here Q is nothing but electric charge, right? So units. So here what are the units of electric current? Units are nothing but, first, numerator. What is numerator? Coulomb. Okay. 1 coulomb per second. that is equals to coulomb per second is the unit of electric current, and that is also now known as 1 ampere. Okay, so what is its charge? I mean unit. So unit is ampere. Okay, its unit is ampere. Fine. Now this is about electric current. Now we have just mentioned that when the circuit is closed, then bulb is glowing, that, and that means all these charges are moving in a particular direction, right? But what makes the electrons to move in a particular direction? Is there any other energy which is acting on it? So there is no, not an energy, there is a force acting on it. Okay. Now what is this force? And I'll tell you what it is. So that is when it is connected to a battery. Okay. Now what's happening here? I've connected it to a battery and then bulb, right? So now the switch is on. So it is positive terminal, negative terminal. So whenever the switch is on, then what's happening throughout this conductor? It is a conductor, right? So throughout this conductor, one electric field is producing. Okay, some electric field will be produced, and what this field is doing? So it is simply exerting some force on these particles. Okay, which particles? The charges which are in motion. So they are nothing but electrons. So this electric field is exerting some force on for these electrons in order to move in a particular direction, right? Now what it is doing? It is simply, it is exerting force. That is nothing but by applying force, these particles are moving in a certain direction, right? So can I write F into S? So electric field exerting some force on it. Okay. So due to this force, they are displacing some distance S. So isn't it nothing but work done that you have learned it in your 9th class? Okay. So work is nothing but the force applied on an object to displace it through a distance S, isn't it? So that is fine. This is for work, but on which it is working? Okay, so which physical quantity is doing work here? Exerting force here, electric force. So I can consider that electric force is working, but working on what? That is also matters. So here it is working on charges, right? So see, by this I can describe a physical quantity. Okay, that is nothing but potential difference. Okay, potential difference. So how do we define this potential difference? Simple. Here what we have identified, that is only the definition of this potential difference. That is nothing but the work done. Okay, work done by what? So whenever we are talking about work done, we need to mention by what the work is done and on which it is. Okay. So here the work done by the electric field. Okay. On charge. Right. On charge. Fine. So this is nothing but potential difference. Got it? So this potential difference is also known as the another word, that is nothing but voltage. Okay, so this voltage and potential difference is denoted by the letter V. Okay, so V is nothing but work done by charge. Okay, so here V is nothing but, I can simply write V is nothing but W by Q. Right, so this is the formula to find potential difference. Now it is also a physical quantity, right? Now what about the units of this potential difference or voltage? Simply the units are just, you need to write the units of work and charge. What is the unit of work? It is nothing but joule, and unit of what it is? Charge. What is unit of charge? It is coulomb. Got it? Now the units of potential difference is nothing but joule per coulomb. But there is also one more term which gives the unit of potential difference, that is nothing but volt. Okay, volt is nothing but joule per coulomb. Okay, so this is the unit of potential difference. And is there any way to measure the current and potential difference in any circuit? Are there any devices? Yes, there are devices to measure potential difference and also electric current. So now the device which is used to measure this potential difference is known as voltmeter. Okay, so voltmeter is the instrument or a device which is used to measure the potential difference in between any 2 points. Okay, we always measure the difference between any 2 points, right? But we have one more uh, I mean device which is used to measure electric current is ammeter. Okay, ammeter. Now what it says, it measures the current in the circuit, right? And we also have one more device, that is galvanometer. Okay, now what is the difference between ammeter and galvanometer? Here, ammeter simply measures the exact amount of current, right? But galvanometer detects the current. Okay, well, if we connect galvanometer to any circuit, then first it detects whether the current flowing through this circuit or not. Okay, if it is yes, okay, if the current passes through the circuit, then it gives the direction. Okay, it detects the current and also it gives the direction of the current. But ammeter only gives the value, exact value of amount of current passing through the circuit. Okay, now I hope you have understood the difference between these two devices. So when according to your purpose, so you can choose the device to measure current. Okay, so these are the devices which are used to measure potential difference and electric current, right? Now it's time to discuss a very similar quantity of this potential difference, that is EMF. Now what is this EMF? Simply it is known as electromotive force, AMF, right? And it is denoted by the letter epsilon, and it is very similar to potential difference. Got it? Now, what is this potential? What is this EMF? So whenever you went to buy an electric appliances, then have you noticed on that appliance that it uses this much power and it gives volts, okay, watts and volts, right? Now that watts gives, for example, now you just bought a bulb, right? I'm just taking the values, okay, for your understanding. Here, the on that bulb you can see 60 watts, okay, and 6 volts. Got it? So this 60 watts gives the power. Okay, it gives the value of power, and this gives not since it has volts, ma'am, volts is nothing but it is a unit of potential difference. So this is nothing but potential difference, but no, it gives the value of EMF. Yes, it also have same units as potential difference, that is volts. Okay, now everything is fine, but what is this EMF exactly, right? So I'll tell you here. To understand this, let's just consider a battery. What's exactly happening inside the battery? Till now we have discussed if we connected it to the battery, then what's happening outside the battery, right? Now it's time for what's happening inside a battery and how exactly is this battery working, right? So whenever you talk about a cell or a battery, then you will be noticing two terminals, right? So what is the positive terminal and where is the negative terminal, right? So this battery has two electrodes. We call this two terminals as two electrodes, right? And in between these electrons, we have an electric, so chemical solution. We call this solution as electrolyte. Got it? So these electrodes are known as terminal. These terminals are known as electrodes. Okay, and in between this, it is filled with electrolyte. Now, what is this electrodes and electrolyte? Electrolyte is a chemical solution, while electrodes are the conductors. Okay. Now, what's happening between these two? Now, electrolyte has some energy, right? Now, what is this? And since it is a chemical solution, it has some tendency to push these all the positive charges are one side. Okay, all the negative charges are one side, right? So it has a ability. So that is known as that is done by chemical force. Okay, here in electrolyte, what's happening? Chemical force is exerting some force on these charges in order to obtain in order to separate all these charges, right? Now that's fine. So since it is started work and it is exerting work and all the positive charges are depositing on one plate and all the negative charges are depositing on one plate. So here we call it as it is a positive terminal and it is a negative terminal. Fine. Now, while the number of charges are depositing on this electrode, then one more energy or one more force acts on it. Okay, that is nothing but electric force. Electric force. Now, what about the relation between forces? These forces, for example, this there is a charge. Okay, there is a positive charge we have here. Now, this electric solution, I mean chemical solution, electrolyte, what it does, it simply pushes it towards positive terminal, right? So this the force on it is chemical force, but it also experiences electric force. So what this electric force do? Simply it opposes its motion. So this electric force acts in this direction. That is, chemical force and electric force have different directions. Now, when these two forces are equal, then this charge won't move, right? So it will be in rest. When Fe is equals to Fc. But if I now when you are buying any battery or cell, this is in this condition. Okay, that cell is in this condition. That means potential difference is equals to electric force is equals to chemical force. But whenever you have attached or connected to any other conductor, for example, now I have connected it to a conductor. Now what happens? Conductor have so many positive charges and negative charges, right? So positive charges won't move, so there is no problem with positive charges. But yes, we do have negative charges, free charges, right? They move randomly here and there. But here, since it is a positive charges, okay, all the positive charges are accumulated on one plate. Now it is connected to this, right? So anyway, it also have negative charges, right? So these negative charges get attracted to positive charges and they'll accumulate on this plate. Okay, now what happens? There is a disturbance in the balance. Now initially, in this plate 10 electrons are there, I mean 10 charges are there, and on this place also 10 charges are there, right? Now both equal and opposite charges are there. Now what happened? Suddenly an electron from the conductor got attracted to this positive terminal. Now the balance is gone. Now here 11 charges are there, but here only 10, right? Now in this case, chemical force increases and this electric force decreases. Now this electric chemical force applies exert force on this negative charge to bring it to the on this negative terminal. Okay, now what chemical force is doing is just exerting force on negative charge so that it can be deposited on negative terminal, right? Now by applying force, it is changing, it is moving some distance, right? Now it is also nothing but force into displacement, right? Now it is also force into displacement. That is nothing but work. But work done by what? Work done by chemical force, right? On what? On charges. Okay, on negative charge here, negative charge it actually works. But in definition, we simply consider it as a positive charge, right? And here it is also positive. Now, this EMF is known as the work done by the chemical force to bring a unit positive charge. Now here, the work done to bring a negative terminal to the positive terminal, or the positive terminal to the negative terminal is same, right? So there is no problem if I consider whether I consider a negative terminal or a positive charge or a negative charge in a definition. So what I'm doing is simply defining it as, observe carefully the definition of potential difference and electromotive force. Here it is the work done. So just I have mentioned earlier, right? So when you're talking about work done, you have to mention work done by what and on which it is done, right? So here work done by chemical force, right? Chemical force on. So I'm considering chemical force on unit positive charge. Okay, unit positive charge. Now, what is the purpose of exerting force on it? Because to bring it from negative terminal to positive terminal. Negative terminal to positive. Okay, so this is nothing but EMF, and it also has same units as potential difference. Now, what is the difference between potential difference and EMF? So there are very few. So let me discuss one by one. So you can see potential difference outside the, so sorry, first let's start from definition. It is work done by electric field, right? Or electric force, you can consider electric force. But in EMF, work done by chemical force, right? Work done by chemical force, right? And you can see this potential difference outside the in the conductor. Okay, in the conductor, in the circuit, you can consider in the conductor, in the circuit, but you can see this EMF inside the battery. Okay, and yes, here also you can write outside the battery. Outside the battery is nothing but in the conductors and in the wires, right? So outside the battery. Got it? So these are the basic differences. And yes, it also has units volts, and this is also has units volts. Fine. And that means work done on charge, and EMF also work done on charge. That's the difference between electric potential difference and EMF, right? Now it's time to discuss the drift velocity. Okay, so till now we are discussing that it is moving from one point to the another point, right? So if any object is moving from one point to another point, then that means it is in motion. Okay, if any object in motion, then it must be moving with some velocity, right? But here in any conductor, there won't be any one or two electrons, right? There may be millions of free charges it have. So we cannot we cannot take one particular charge and simply find its velocity, right? It is meaningless. So we can consider an average velocity of all the charges in a conductor, right? So that is known as drift velocity. Okay, average velocity or average speed of electrons or all charges, right? So this is denoted by the letter Vd. Okay, and there is a derivation of this particular quantity in our textbook, but since it is a revision, we only need to focus on basic points. Okay, so what is the formula for this drift velocity? It is nothing but Vd is equals to I by nqa. Okay, Now I'll tell you what is this. For example, there is a conductor. Okay, so there is a conductor of length L. Okay, its length, its whole length from here to here is L, point A and point B. Right now, number of charges are moving through this cross section. Okay, we need to take a cross section, right? So now I have considered this cross section, and the area of this cross section is A. Right now, n number of electrons are moving from A to B. Right, that is charge. Now, if n number of charges are flowing through this cross section, that is nothing but current. Okay, that is current. Now here, sometimes they may ask you that define, write the drift velocity, write the formula of drift velocity, and tell me about each and every term in it. So here, that question may becomes for 1 mark or 2 marks. I guess I'll tell you it in about it in previous year questions. We do have that series also, right? Yes. Here, I is nothing but electric current, N is number of charges, Q is charge, and here A is area of cross section, right? Instead of charge, what are these charges in motion? They are nothing but electrons, right? So I can write, so I'm simply writing what is I. I is equals to, you simply take all this denominator to the LHS, right? Now it will become NEAVD, right? So here you can say, if you consider positive charges, okay, if you consider negative positive charges, then what happens? It is a constant, area is a constant. Then in order to find this charge positive, in order to maintain the sign of this electric current positive, then velocity should be positive, right? But if we consider this negative, but in order to consider this positive, then it will be velocity also has to negative, right? So here you can understand that. So electrons direction of these charges. So what is the flow of current? Current always goes from. So here I'm just neglecting this. Okay, direction of flow. Current always goes from high potential to low potential. High potential to low potential, right? Now, what is the current direction? Current direction is high to low. Okay. Then what about electrons direction? Electrons direction is opposite to current's direction. So that is low to high. Got it? And positive charges. Positive charges direction is same as current. So we can consider, technically there is no direction, there is no motion of charges, positive charges. But here it is electric charge, electrons and positive charges have both the opposite direction, right? That's why we have done it. And here the main point here to understand is electrons and current both have different directions, I mean opposite directions. Got it? So this is the relation between drift velocity and current. Okay, these two are same. Got it? And it's time to discuss after potential difference and electromotive force. It's time to discuss Ohm's law, the very important law. Okay. Now, what this law says? Okay, Ohm's law. Yes, what this law says. So, in order to understand this, let's discuss a small activity. Okay. Now, what's that activity? Here, we just considered a small circuit which has a battery, okay, and an ammeter. Okay, let's just say a switch 2 and an ammeter. Okay. Now, I have taken any device. Okay. Let's just take, I have taken one conductor. Okay, one conductor of this length. Okay, and I have just closed the circuit. I've closed this circuit, and since I have considered an ammeter to measure current, right? And also I am just taking one voltmeter. Okay, voltmeter has to connect parallelly while ammeter has to connect in series. I'll tell you why it is in parallel and why ammeter is in series. In later, electric circuit where we'll discuss electric circuit, right? Now, in this circuit, what's happening? I have taken a battery, switch, ammeter, voltmeter, a device, and connecting wires, right? Now, when I close this switch, it is positive terminal and negative terminal. When I off this switch, then circuit will be closed. Now, electric current flows through it, right? Now, when electric current is flows through, then you can measure the current value here, okay, and potential difference here, right? So you can note take a table for these two values. So to write the potential difference, it is V, and to write the current values, it is I. So if you just if you note it down all the cases in this table, then you'll get a clear idea. So first to take one battery, okay, one 5 volts battery, or you can simply take 1.5 volts battery, okay. In first case, when it is 1.51, so take V1 as it is, and when we have connected, when we have added 1.5 volt battery to the circuit, then we can see that reading in our ammeter, right? That value will be V1, and that's fine. Now next case, again add one more 1.5, okay. Next case, again one more 1.5, then it will be 3 volts battery, and you will get on another reading in ammeter, that is I2, right? If you keep on continuing this activity for several cases, then you will be understanding that the ratio of V and I of every case is very similar, okay. So after performing this activity for several times, so the scientist Ohm decided that, so this ratio V by I ratio is always constant, no matter the value of this battery, right? So this value is always, so this V is directly proportional to I. So whenever we are performing this activity, the temperature is constant, right? At a constant temperature, at a constant temperature, potential difference between two ends of this conductor is equals to the current passing, is directly proportional to the current passing through it. So this is the statement of Ohm's law. Okay, I hope I don't need to write it here. So since I am telling it once again, so here potential Ohm's law states that, okay, I'll just write it. So statement. What is Ohm's law statement? So in statement, don't ever forget to write at a constant temperature. Right? At a constant temperature. So what's happening at this constant temperature? The potential difference between the ends of what? Ends of a conductor. Okay, the conductor, whatever we have taken, ends of the conductor is directly proportional to, symbol. Okay, this is a symbol proportional to the electric current passing through it. Okay, passing through that conductor. Okay, passing through it. This is the definition. And from this definition, if I want to express it in mathematically, then I can write V is directly proportional to I, right? So just remove this proportionality constant, then you will be able to see one, we will be able to get one a proportionality constant, that is nothing but I into R. So this R is nothing but proportionality constant. Also, it has some very special importance, and it is a physical quantity too, that is resistance. Okay, now the relation between potential difference and current is I is equals to V by R, we can write. Okay, from this I can, how many ways I can write it? Either I can write V is equals to IR, or else I is equals to V by R. Just bring that R to the other side. Okay, and also I can write R is equals to V by I. right? So these are all the ways to express Ohm's law, right? Now, what about this? The materials which obey the Ohm's law and which does not obey the Ohm's law. Okay, there are two types of materials, materials which obeys this Ohm's law and which does not obey the Ohm's law. For example, Ohm's law, what Ohm's law says? P is directly proportional to I, right? So there are some materials which obeys Ohm's law. They are known as ohmic conductors. Okay, ohmic conductors. And the materials which does not obey the Ohm's law are known as non-ohmic conductors, right? And if I write graph for graph between current and voltage for these two cases, then I'll get graph like this for Ohm's law. It is I and it is V. Okay. Then on x-axis I have considered all the voltage values. On y-axis I have taken all the current values, right? Now I'll get graph like this for ohmic conductors. Then what about it for non-ohmic conductors? Anyway, these don't obey, right? So we'll get graph like this. So this is I, on y-axis I, it is y, on x-axis it is x, right? So this is how we got graph for both cases. So in ohmic conductors we get linear graph. Okay, linear graph, and here it is a non-linear graph. Got it? And can you give me some examples of ohmic conductors and non-ohmic conductors in comment section? I hope to receive all the comments. Okay. Now, this is about ohmic conductors and non-ohmic conductors, right? Now, what is this proportionality constants importance? Okay. Why do we have a separate name for it and even separate limits and units too? So let's discuss about resistance. So what is that quantity? That quantity is nothing but resistance. Now, what is this resistance? So, in every material, if we consider, if we observe, when current passing through that conductor, then there may be some opposition to the flow of charges, right? So, some may allow the current to pass through it, and some may not allow current, right? Now, the materials which are not allowing the current to pass through them are literally offering some what obstruction, right? Some opposition to the flow of these charges. Now, this property is known as resistance. Okay. Now, what is this charge resistance? Resistance is the property of opposition or obstruction. Okay, obstruction offered. Obstruction offered to the flow of charges in a conductor or in a material. Okay, this is the material's property. Got it? And this resistance depends on some factors. What are those factors? There are 4 factors it depends on, and 4 important factors. So they are, first one, if resistance, okay, before that let's just know the units. So units of this resistance is ohm. Okay, ohms, and that is denoted by the letter symbol this. Okay, since it is a proportionality constant of Ohm's law, it has a units ohm. Got it? Now, the factors which depends on it. Okay, on which it depends. Sorry. So first, the nature of the material. Okay. So if it is a plastic, it shows it has some resistance. If it is a metal, it has some resistance, right? So it depends on the nature of the material. And the next thing is temperature. Okay, it depends on temperature. That means resistance increases with the temperature, right? And the third one is length of the conductor. Okay, now if length increases, then what happens to the resistance? Simply, if length increases, then resistance also increases. Length of the conductor. And also one more physical quantity of conductor on which this resistance depends, that is nothing but area of cross section. Okay. So this is also, but it is reverse. Okay, here resistance is directly proportional to length, right? And here the area of cross section, and this resistance is inversely proportional to area of cross section. So from these two, I can simply write R is directly proportional to length and also inversely proportional to area, right? So if I just remove this constant, proportionality constant, then I'll get R is equals to rho L by A, right? And here too, this proportionality constant rho is nothing but resistivity. Resistivity. Okay, it has the units ohm meter. Okay, we can simply write from this what is rho. Here rho is nothing but R into A by L. Got it? This is rho. And this resistivity is inversely proportional to, or you can say, conductivity. Conductivity is denoted by sigma. Fine. So this is about resistance, the factors on which it depends, and also resistivity. Right. Now this resistance is a property. Okay, resistivity is it gives the information about how much the taken given material shows resistance per unit length and per unit cross section. Okay, but the resistance depends on nature and temperature also, but resistivity only depends on length and area. Got it? Nature. And here one more thing is the units of resistance is ohm meter, when the units of resistance is ohm. Got it? Now this is about resistance. On this resistance, based on this resistance, we can divide all the materials all in three types. Okay, what are they? Okay, resistance decides the material type. Now, if the resistance is very less, then those materials are known as conductors. Okay, conductors, insulators, and semiconductors. Okay, so here in conductors, resistance is very less. R is very less. Okay, it is of order 10 to the power of minus 4 ohm to 10 to the power of minus 6 ohms. This is the conductors have this much resistance. But when it comes to insulators, R is very high. Okay, more resistance it offers. So resistance order is of 10 to the power of minus 16. It can be of 10 to the power of minus 16 or minus 14 to 10 to the power of minus 16 ohms, right? So it is the very highest electric resistance. Okay, now what about semiconductors? Semiconductors are intermediate state between these insulators and electric conductors. Now these semiconductors resistance lies between 10 to the power of, it is more than conductors resistivity and less than insulators resistivity. I hope you got it. So its resistance is greater than 10 to the power of minus 4. Okay, minus 4 to 10 to the power of minus 6 ohms, and its resistivity is less than 10 to the power of minus 14 ohms. Got it? And some examples of conductors. All metals. All metals are very good examples of conductors. Then what about insulators? Insulators, you can take wood. Okay, wood and cloths. Okay, and then paper. These are some examples of insulators. And also in conductors, human body is also very good conductor. Human body is electrically conductor and optical insulator. Fine. And semiconductors are all the impure materials like gallium, okay, silicon. These are the examples of semiconductor, right? So now we have completed discussing Ohm's law and the related topic resistance and the factors on which it depends, right? So it is all about Ohm's law. Now, what about electric shock? Have you ever listened uh, it in news? So you might have mostly listened it and heard it in news. Now, what is this electric shock? So shock is generally it is disturbance made by the flow of electric current in our human body, right? So then only we say I got shocked, right? So why this shock happens? So whenever there is a change in, so when there is a change in potential difference, when there is a difference in potential difference between parts of human body, then what happens? So due to this potential difference, what happens? Current flows, right? But to which the current flows? So the current can have two paths when it comes to human body. It can pass through out of the, outside the body. That means through skins. Okay, through skin it can flow, but and also it has one more part, that is our organs. Okay, it can also pass through organs, but in between these two, current always chooses to pass through organs because skin offers more resistance, but organs offer less resistance than skin. So the current always pass through organs. So whenever current passes through our body parts, human organs, then it creates some disturbance. Okay, it creates disturbance. So this disturbance is known as electric shock. Electric shock. Got it? And if, for example, if this current is very low, like 0.001, then we can just felt it. Got it? But if it is for 0.005, then it is little bit painful. So we can experience of pain, right? But if it is little more increased and now it is 0.01, then it causes and we just lose control. Okay, sorry, muscle contractions we can experience, and if it is 0.015, then we will lose control. And now if it is 0.07, and even if it is if the current passes through our heart for 1 second with this amount of electric current, then the person can die. Okay, the heart stops functioning. Okay, so on this case, a person can die. Got it? So this is how dangerous electric shock is. So always you need to take precautions whenever you are feeling some current leakages, okay, or repairs, and especially in rainy days, rainy season. Got it? So this is about electric shock. And coming to the last topic of this chapter, and also very interesting and important topic, that is electric circuits and Kirchhoff laws. Okay, these two are interrelated topics. Now let's start electric circuits. Yes, what is this electric circuit? Okay, circuit is simply, it is nothing but it is a closed path we are showing electrons to pass through. Okay, so now we are giving the directions to what? Free charges in a conductor, right? That is nothing but electric circuit. It is a closed path. And now there are a few types. We have two types of electric circuits. Okay, combinations. They are nothing but series combination and uh, parallel combination. First, we are going to discuss series combination. Okay. Now, what is this series? For example, I have some. For example, I have three resistors. Okay. Now I want to combine it. I want to connect it with each other. Now, how can I combine? First, I want to combine it in this way. Okay. It is one electric resistor, and this is another one, and this is the last one I have. Now it has a resistance R1, it has a resistance R2, and it has resistance R3. Now all these resistors are connected to a battery of V. Got it? Now this is positive terminal and negative terminal. Now current flows through it. So the current flowing through it is I. So here this combination is known as series combination. Now what's happening in this series combination? Now in this combination, a current is flowing through it, right? So anywhere, if you take any point, then current is constant. So here in series combination, one device is attached to another device, and one end of the device attached to another end of the uh, device, right? One more device, right? So in this combination is known as where all these devices are connecting one on one end of the another. So this combination is known as series combination, and in this combination, current of all for all the points in the circuit is constant. Okay, now what is the varying constant? So varying constant is V. Now V is nothing but potential difference, right? Potential difference between these 2 points is V1, and potential difference between these 2 points is V2, and potential difference between these 2 points is V3, right? So potential difference is a variable. Okay, so these 2 points are very important. They may ask you in part B, right? Now the resultant resistance. Okay, so the resultant resistance is nothing but R is equals to resultant resistance in series is equals to R1 plus R2 plus R3. Okay, if you want to find this derivation, then yes, let's simply write it. So it is very short. So here what it is, current is a very constant term, but it is a variable, right? Now the potential difference between these 2 points A to B is nothing but V, right? Now this potential difference is equals to sum of these three, right? Now I can write V potential difference is equals to total potential difference is equals to V1 plus V2 plus V3. But we have already studied from in Ohm's law that V is equals to IR, right? Now simply V is equals to IR. S is nothing but total resistance. V1 is equals to I is constant, right? So I can simply take current passing through this resistance is I, and R1 is the resistance of this resistor. Now V2 is nothing but IR2, and V3 is nothing but IR3. Now if I take I common from all these terms from RHS, then I remained with R1 plus R2 plus R3, right? So here I from RHS and I from LHS got cancelled. Then I left with the terms resultant resistance is equals to R1 plus R2 plus R3. Simply it is the algebraic sum of all the resistance in the circuit, right? So this is LS series. Now an ammeter has to connect in series combination in order to measure uh, the current through circuit, total circuit. Ammeter has to connect in series. Now it's time to discuss second combination, that is parallel combination. Now what about this parallel combination? How all the devices are connected in this combination? Just simply let's take again those three resistors in this case too, but in this case this time we are gonna uh, connect it like this. So this is my first resistor, This is my second resistor, and this is my third resistor. Okay. Now all these ends are connected to one terminal, and all this another ends connected to another terminal, right? Now I'm going to connect these 2 points to one battery. Fine. Now this is the first resistance, and its resistance is R1, R2, and R3. Right now, since I have connected it to battery, the current passing through it is I. Right. So whenever till here I current came. Now at this point I got divided into three parts. That is, here on this device I1 current is passing, and here I2 current, and here I3 current is passing, right? But if you consider between any 2 points, okay, so from here to here same voltage will be there, and from here to here same voltage, and between these 2 points same voltage is there, right? So in this connection, in this combination, the constant one is voltage. Voltage is constant throughout the circuit between any 2 points, but current, electric current is variable, okay, from point to point here. So if you take I is got divided into three parts, right? So I can simply write this as I can write mathematically as I is equals to I1 plus I2 plus I3, right? But we already know I is equals to what? V by R. Now I can simply write I is current in complete circuit. So, and voltage is same, right? I can simply write V by R P, resistance in parallel combination, and again V by R1, resistance of first resistor, and V by R2, and I3 is V by R3. Now if you take V common from all the terms from of left side and right side of the equation, then you remain with 1 by R equivalent resistance is equals to 1 by R1, 1 by R2 plus 1 by R3. So here in parallel combination, you just need to add the reciprocals of each and every resistor individually, right? So this is about the equivalent resistance in parallel combination, and voltage and current. So voltage has to connect parallelly, okay, in parallel combination to any object, because any device, because we need to measure the potential difference between 2 points, right? So to connect it, I have to connect the voltage here to here. So it is nothing but a parallel combination. Now you might have understood why we have to connect the ammeter in series and the voltmeter in parallel. Okay, there are some problems on series and the parallel combination, but we in this video we are not going to discuss any numericals. I'll try to post one more video from this chapter only dedicated to numericals, because we can expect some numericals in the board final exams from this chapter. Okay, from it can be from Kirchhoff laws, it can be from Ohm's law. Okay, there are so many topics we can expect the problems from. Okay, now the last topic is nothing but a very interesting topic, that is Kirchhoff laws. Okay, Kirchhoff's laws. Kirchhoff's laws are, there are two laws we have. So they got divided into two types. So they are junction law, and one more is loop law. Okay, loop law. Now let's discuss them separately. What this loop law says and what this junction law says. Loop law says that if it is a junction, then all the currents are coming to this junction are equals to the going out of the junction. For example, it is I1, I2, I3, I4, and I5. Now I can write at this junction there are no currents it can hold. So whatever the amount of current passing towards the junction is equals to the same current leaving away from the junction. So I can write I1 is coming towards the junction plus I2 is coming towards the junction, and that is equals to I3 plus I4 plus I5, right? If I just write all this here, then it will become I is equals to 0, right? So here it is algebraic sum of all the currents coming towards the junction is equals to all the currents going away from the junction, right? So this is known as junction law, and it is based on what? Law of conservation of charge. Law of conservation of charge. Okay, now it's time to discuss loop law. For example, if we consider any series combination, okay, so now if we just considering any object, so it is a one resistor, and it is one more resistor, and I have connected it to the battery, right? So this is my circuit. Now it is all the devices are connected in series, right? So in series, current I is constant, but V varies, right? So varies between any 2 points. For example, here it is V1, here it is V2, and it is V. But whatever the difference, but every some at some points this voltage may increase, and another some points the voltage may decrease. But as a whole, if I just consider loop from A, B, C, D, A, B, C, D, A, this loop, if I consider this loop, then the algebraic sum of all the voltages of individual voltages is equals to 0. Okay, this is loop law, right? And this is based on the law of conservation of energy. Law of conservation of energy. Got it? Now, for this loop law, to apply this loop law, you need to know some conventions. Okay. So generally, loop junction law is known as KCL, and this loop law is known as KVL, Kirchhoff's voltage law, right? So KVL rules we can consider. So whenever, if in a circuit, for example, you are going from positive terminal to, it is a positive terminal and it is a negative terminal. You are going from positive terminal to negative terminal, then the voltage is negative. Okay. But if you are going from negative terminal to positive terminal, then your voltage is positive. Okay. This is for battery. Now what it is for a resistor? Okay. For example, this is resistor. Okay. I current is flowing from point A to point B. Okay. I current direction is this. But if you are going in the same direction of current, then your voltage is negative. Okay, here it is negative. But if you are going opposite direction to the current direction, then your voltage is positive, right? For example, let's just take a small circuit. Okay, that is, it is one circuit resistor, and it is one another resistor, and this is battery, right? Okay, so here it is R1 and R2, and it is positive terminal, negative terminal, and current is going from this to this, right? Now here it has a voltage V. Now we need to apply KVL now, but I am going in this direction from this point A. Okay, from this point A, it is a B, it is C, it is D. Now I have to apply loop law for the loop A, B, C, D, A, right? Now first I'm starting from here, so I'm going this way. Current is going in also this way, but I'm in the direction of current, so I'll get minus right, minus B. So that is minus I R1. And same for the resistor, second resistor also, that is minus I R2, right? And after coming this from till here, you have came here, and now you are just going from negative terminal to positive, right? So when it is negative to positive, then you'll be having positive term, voltage, right? So it is V and is equals to 0, right? So this is how you need to apply KVL rule. Got it? So guys, this is about Kirchhoff's loop law and Kirchhoff's voltage law, right? So with this, we have completed Kirchhoff laws. And a last small topic is there, that is power. Now, what is power? What do you mean power? Power is simply nothing but the rate of, in earlier classes, in ninth class, you might have studied work, energy, and yes, power, right? So their work power is nothing but rate of doing work, right? Here, power is nothing but rate of consumption of energy. Okay, consumption of which energy? What is it? Electrical energy. Okay, rate of consumption of electrical energy. Right? So this is the definition of electric current, and how do we represent it? How do we find it? So it is simply the product of voltage and current, right? And we also have a relation between V is equals to IR, right? If you substitute here in I, okay, in the place of V, then you will get V is equals to I square R, right? And also you have one more, one more relation, that V is equal, I is equals to V by R. So if you substitute here, then again you will get V square by R. Okay, so this is the formula to find a power of any relation. Got it? But what is the unit of this power? Okay, unit of this power consumption is nothing but watt. Okay, watt is a very small unit, but the power we are consuming at our homes will be measured by the unit itself. Okay, 1 unit is equals to 1 kilowatt and 1 kilowatt hour. Okay, and that is equals to 1 kilo is nothing but 1,000, right? And watt is simply watt only, and hour is nothing but 3600 second, right? So that is nothing but 3600 second. If I just combine all it, then 36 into 10 to the power of 5 watt second. Or we can also write 3.6 into 10 to the power of 6 watt second, right? This is 1 unit value. They may ask you it in MCQs as well, so note it down. So this is 1 kilo power definition and units, right? So guys, this is about power. And if I talk about the connections at our home, then all the connections are at our home are in series connection. Oh, no, it is in parallel connection. Sorry, parallel connection. Because, for example, we have so many appliances at our home, right? So we may have bulb, okay, and also TV and fans, okay, and washing machine or refrigerator. Okay, we have all these appliances at our home. Now, if I just connected all these in a series combination, okay, it is connected to this way, okay, and I have connected it to one battery here. Then what happens? Here it is a negative terminal and it is a positive terminal. Now, whenever this switch is on, then simply current passes through all the appliances at our home, right? But sometimes we don't need all we don't need all the appliances to work. For example, it is a daytime. I don't want to use my bulb. Okay, only I want to use fan, refrigerator, and TV. Okay, sometimes I want to sleep. Now at that time I don't want to watch TV, so I want to switch off TV, but I cannot do it in a series combination. And for example, the main important point is that, for example, my fan got damaged. Okay, now I want to use all my refrigerator, TV, and bulb. So if it is damaged, then I cannot use the other appliances also, because if it is damaged, then the circuit will be open, so current will not flow through it. right? So to avoid all these problems, we simply connect all these appliances in a parallel combination, right? So I'm just connecting all these in a parallel combination. Okay. Now, since all these are in parallel, so there is no problem even if one got damaged. Okay. It is positive terminal and it is negative terminal. Now current is passing through all. Now if I just fix a switch here, okay. If I just fix a switch here, okay, switch here, here, and here too. Now, if I want to on bulb, I just only need to switch on this, right? And if I don't want to use it, I can just switch off it, right? So there is a facility in parallel combination, which is not in series combination, right? So that is why all appliances at our home are made connected in parallel. But there is a minimum and maximum limit of current usage of current consumption of these all appliances, right? So the minimum current we use at the home is 5 amperes, right? And the maximum current we use is 20 amperes. So this is minimum and this is maximum. Now, what happens if 21 ampere current passing through at our home? Now, what happens? All these appliances cannot bear this much of electricity, right? So we at this time they got damaged. All the appliances feel overloaded. Okay, this is the situation called overload. Overload means the maximum it experiences the electric current more than their limit, right? So that is the case overload. At this case, all the electric appliances got damaged. Okay, so to avoid this problem, we need to use one more electric appliances called fuse. Okay, so what is this fuse? Fuse is simply a thin wire. Okay, a thin wire whose melting point is more. Sorry, melting point is very less. That means for a very small amount of heat also it melts, and also high resistance. So resistance of this wire should be more, right? So this is a fuse. If we connect it to the in series with a live wire, okay, we need to connect this series with live wire in our meter. Okay, then it resists the current if more amount of current is passing through that meter. Then first of all, this fuse resists the current. Here we can use fuse. Okay, now through this, if 21 amperes of current is passing through it, then what happens? Anyway, fuse has high resistance, right? So it resists the current. So when it is resisting, it gets heated, right? Whenever something is resistance is opposing force is acting on it, then it gets heated. So since it has a low melting point, so for that temperature also this wire got melts. So since it is melted, so there is a gap in the circuit. So there won't be any passage in the current through our home appliances, right? So this is how we can protect our home appliances from overloading. Got it? So guys, this is about it, and I hope we have covered all the topics in this video. So we have covered electric current, okay, and potential difference and EMF, right? And after that, we have discussed Ohm's law. Fine. And then we have discussed about resistance and on factors it resists, and it depends, and also the specific resistance, that's nothing but resistivity, right? After that, we have discussed about electric circuits, and then Kirchhoff laws, right? And at last, we have discussed about power. So I hope I have covered all the topics in this video, and if you feel anything left or anything we have skipped or missed, then please let me know in the comment section. And also I want your feedback, right, guys, so that it will make me feel that up to what level you are able to understanding and following my videos, and what exactly you are expecting from YouTube, so that I can provide it or not. So I want all your feedback about this video. And if you like the video and if you understand the whole chapter, then like this video and also subscribe to the channel. Okay, so we'll meet in the next one more important chapter, that is electromagnetism. Okay, that is also a bit lengthy chapter, but still we will discuss it in a easy manner. Got it? So until then, keep learning, and all the best, guys.